Hi everyone, thank you for being here to attend my presentation. Today I'm going to be talking about Crescendo, a self-paced programming environment that helps and supports novice students. Firstly, I'd like to invite you to go to this link. Go SIGCSE'20/Crescendo. It's a Google Doc link where you can write down your questions, ideas, and feedback. I'm in the doc and I'll answer your questions after the presentation. First, I'll talk about the previous work and why we built the system. In introductory programming practices, students can easily get stuck and feel frustrated. To learn programming efficiently, students need support that are engaging enough to keep them motivated, and they also need real-time support to help them get unstuck and learn necessary programming skills. There are two programming environments that are most common and effective: block-based programming environments and drill and practice programming environments. Different from text-based programming environments, block-based environments such as Scratch, Alice, and Snap. They feature using blocks instead of codes, minimizing possibilities of syntax errors, and make it possible for novices with only months or weeks or even days of experience to build complex apps and games. So the visual and the interactive output, the block-based language, as well as the open-ended tasks has enabled the block-based environment to be engaged and promotes long-term interest. In fact, one of our co-authors, Lido and colleagues, conducted an experiment where undergraduate students were offered pathfinding visualization throughout 2 semesters. Many of them reported that visualization was easy and fun. Also, one chart and colleagues found that comparing to text-based programming, high school computer science students were more interested in taking future CS courses after doing block-based programming tasks. One of the ways these systems are engaging is because they enable students to create anything they want, in another word, to build open-ended, creative programs. For example, this is a game design that a pair of students submitted for after only 2 months of introductory programming course. As you can see from some of the rest of the submissions, students created a variety of different game designs in Snap. So to recap, we find evidence from prior research and our experience that the block-based language, visual and interactive output, as well as the open-endedness has made the block-based environment engaging. While these environments are great because they're open-ended and students can make anything they want, when students are first learning how to program, it's not clear whether being able to make anything you want is actually good. For example, consider this flag exercise. Students are asked to draw a flag they want, but in addition to knowing the programming concepts of how to draw a flag, they also have to make a decision about which flag they want to draw, and they may not understand what properties of the flag make it easier or harder to draw. For example, the flag of Japan requires drawing a circle, which may require geometric and programming skills that a student doesn't have yet. Similarly, in the CS0 course project that we introduced previously, students are allowed to make any game they want. Although the project is well designed and were only assigned to the students after more than 1 month of programming experience, it requires a lot of scaffolding from the instructors to identify what sorts of programming tasks might be appropriate for the skill level of the students. These open-endedness could impose additional challenge for novice students. In fact, Lee and colleagues has described a study where students barely learned anything from open-ended programming. They compared students' experience in an open-ended puzzle design in Gidget, as well as a structured programming practice in Code Academy. They found that students' learning doubled in the Code Academy group, but had no learning gain in the open-ended puzzle design group. This limited learning could be caused by habits of making poorly structured programs. For example, Mirbon Salon and colleagues, in their paper Habits of Scratch Programming, found that students can easily employ an extremely bottom-up approach while doing Scratch programming, in which they start from dragging all the blocks to the code to the block editor without really understanding the meaning of the block or the reason why they are dragging that block to the editor. So how can we create a similar level of engagement with a more scaffolded solution structure? We find several features within drill and practice programming environments that offer such learning opportunities. In contrast to block-based programming, which hosts open-ended tasks, drill and practice system features smaller and closed-ended tasks grouped by concept categories. For example, in this example, in Code Workout, a drill and practice programming environment, we can find programming tasks that are grouped into categories such as recursion, list, abstract data type, and binary tree. The closed-endedness of this task within drill and practice system allows the integration of immediate feedback. Systems that test such immediate feedback, such as coding bats and code workout examples, have been well received among programming students. Kasakuma and colleagues evaluated students' experience using misconception-driven feedback over 3 semesters. They found that comparing to those students who did not use the feedback, students using automatic feedback significantly performed better in the post-test only after 2 classes of instruction. But to provide that feedback, we have to know what the solution looks like, and it has to be a closed-ended problem. Revising our design goal, the closed-endedness task, isolated concepts, and automated feedback provide specific assistance while students are stuck, so they offer more supportive programming experience. To combine the engagement offered by block-based environments as well as the structured programming experience offered by drill and practice environments, here we present Crescendo. It is a system where students could practice closed-ended tasks to learn specific programming concepts, but in a block-based programming environment. It is now available through this link. Learning in Crescendo is organized into a hierarchy, concepts, challenges, and tasks. It organizes small programming tasks into challenges and concepts, such as loops and conditionals. Each concept may have multiple challenges. As a prototype of our content design, we designed 6 challenges. 3 are loops and 3 are conditionals. Each challenge inside a concept also covers a specific learning objective. For example, to complete Loops 1 tasks, students need to understand that loops repeat code sequentially a given number of times. This is a demo of the students working on the Create task of the Loops 1 challenge. The instruction asks students to use the starter code to draw a set of monster teeth, which is composed of combinations of squares and triangles. To complete this task, the students need to understand how to sequentially draw the squares and triangles, and also how to repeat these patterns. To complete Loops 2, students need to understand how to combine codes inside and outside of loops. For example, this is the Create task of the Loops 2 challenge. In this task, students were asked to draw a set of shapes that change colors with gaps. In order to change colors after drawing each shape, the students need to understand the previous programming objective, which is to repeat code inside loops. But to draw 2 gaps, the students also need to understand how to draw gaps before the loop starts and after the loop ends. To finish Loops 3, students should know how to differentiate patterns inside nested loops. For example, in this task, students need to use the inner and outer loops to draw from 1 triangle to the 20 triangles, with 15 triangles in each row. We can see that each challenge introduces a small new skill and is built on the skill acquired by the previous challenge. Here are the stages of all the challenges we have designed. We wanted our tasks to be engaging but maximizing the amount of visual and interactive programming experience. As you can see from our previous code examples, we also want the code to be short for each assignment because we want to give the student a feeling of consistent progression to avoid getting stuck on each and any of the problem and to be able to keep the problem short enough to provide accurate feedback. Inside each challenge, there are 3 tasks. Each challenge has 3 tasks following the idea of use, modify, create. The Use Modify Create framework leads students to progress from existing program to a less scaffolded program. Our co-author Lito and colleagues found that students in the Use Modify Create following curriculum compared to those without finished tasks faster and helped them to build their sense of ownership over the programming artifacts they created. The use task asks the students to run an existing program, understand its output, and sometimes make a small modification. For example, in this use task, students only need to change the literal input in order to create the shapes shown in the instructions. The modify task in Crescendo gives students incomplete or incorrect code. For example, in the modify task here, students only need to change the color of the triangle inside each row and change the size of the pen between each row. The create task asks students to design their own code independently, giving them minimal help or support. For example, here, the students were only given a starter code that draws one triangle, but they are using that to draw the zigzag shape in the instruction panel. So how do we support students inside a task? This picture shows an example of the interface of the task. Crescendo augments and revises the Snap programming interface with 3 important changes. Parsons problem, simplify Snap interface, and the Check My Work automated feedback. Parsons problem breaks a correct solution into code pieces and requires the student to rearrange those mixed-up codes to create the original solution. We implemented Parsons problem because our prior work has shown that students achieve the same learning gains in half of the time using Parsons problems. This picture shows the Parsons problem design. On the left is the original Snap block editor. On the right is our Parsons problem design. We adapted the Parsons problem design from our prior work and to simplify students' experience. We have made the block input non-editable and only offering blocks that students need. We also removed interface elements that are unnecessary or irrelevant. To simplify students' experience, they were also provided with only 1 or 2 lines of instructions with images in each task. In each task, students can click on the Check My Work button to check their work. They can click on the check button, or they can also run their code to update the stars. The objectives they have completed are shown in the golden stars, and the objectives they have not are shown in the hollow stars. The drop-down output of the Check My Work button gives students an overview of the objectives they have or have not completed. Our feedback was generated using static analysis because the tasks are simple and self-contained. We can detect these objectives automatically. When a student finishes the last objectives, all stars will be activated and a Continue button shows up, allowing the student to click on it and move on to the next task. So to recap, when you start Crescendo, you click on the challenge, and that puts you into Use Modify Create. And as you write your code, you get feedback, and when you're done, you progress. Crescendo was used as a programming practice material in 2 settings, an activity in the middle school summer camp, and a homework assignment for an undergraduate SIGCSE'20 course. Both groups of students had had only 1 hour's exposure to Snap programming beforehand. Throughout our user study, we wanted to find out whether Crescendo achieves its goal to offer an engaging and supportive programming experience. We have found high completion rate, quick progression, and continuous engagement among our students. We noticed that most students made to the end of the practice series. In the CS0 homework group, no one was monitored during the students' progress. While this was an assigned homework and students get credit for it, this is a much higher completion rate than the other course homework. In the CS0 homework, while our goal was to see the students feel supported enough by Crescendo to keep going, we did find that students, while working independently, they were still able to progress when get stuck. We also calculated the average time students took to finish each task in Crescendo. We noticed that most tasks took a fairly short amount of time, which is between 1 to 5 minutes. This is in accordance with our design goal, which is to keep students a feeling of consistent progression to avoid them getting stuck on any one problem. To understand students' perceptions of the experience, we also prompted to answer some rating questions asking about their ratings of difficulty, helpfulness, and engagement of the task they have just completed. We saw an increased engagement level as is shown on the green line. The x-axis are the 9 consecutive tasks in the loops concept that they were asked for rating. The last 3 are optional tasks, although we still received 60% of the responses. We also want to understand how they perceive their experience with Crescendo overall. So we asked them, this version of Snap is different from the one that you use in the class. How much do you agree with the following statement? The version of Snap is more motivating for me. The version of Snap is more helpful to me. Among 48 students from whom we have collected the answers, many agreed or strongly agreed that learning in Crescendo is more helpful, as well as more motivating. We have found 30 students in the CS0 course successfully completed the optional third challenge. This challenge was not even for extra credit, so this suggested that the students were engaged enough with Crescendo to continue working voluntarily. So it is possible for Crescendo to allow students to have a both engaged and supported programming experience. Our results have also given us both positive and negative takeaways. For example, one concern with moving from open-ended tasks to closed-ended ones was that it might reduce students' engagement. But our rating results show that most students found Crescendo more engaging than their regular, more open-ended lab experience. Additionally, many CS0 students were engaged enough to complete the optional tasks in Crescendo. This suggests that we can still reap the benefits of visual interactive programming even in a quick and closed-ended task. Within the challenge from the use, modify to create, we found an increasing self-rated difficulty as we shown in our previous slide. The red line is students' rating of difficulty. You can clearly see the use modify create progressions, but also that the tasks themselves are getting more difficult. The use sometimes have a less difficulty than the prior create. While students perceive the increased difficulty, they did not take more than 5 minutes to complete most of the tasks, suggesting that they learned necessary skills to tackle the difficult levels. This is consistent with the theory of zone of proximal development, which encourages tutors to keep students working on the tasks at the edge of their ability while offering scaffolded instructions to allow them to accomplish these tasks. So in both Camp and the CS0 homework activities, we also observed that students were able to progress independently through Crescendo tasks, with most students able to finish the task within the given amount of time, receiving minimal help from the instructors. The instructors also welcome Crescendo as it allowed them to become facilitators of knowledge instead of lecturers because students could progress independently. We have also found a deficiency of our system. We found that in our middle school classroom, students accumulated bigger and bigger differences, and the slower students would get anxious when they were left behind. In the future, we want to make Crescendo to support pair programming and as well as give students more encouragement and positive feedback in the future task design to help lower performing students still feel motivated to progress inside the system. Thank you for listening. Please, if you have any feedback or questions, don't forget to add them to the Google Doc. Thanks. Bye.